The Oxygen Hemoglobin Dissociation Curve by Kenneth Holmes. Hemoglobin is located in red blood cells, where there are roughly 270 million hemoglobin per red blood cell. They are responsible for transporting oxygen to tissues throughout the body and dropping off CO2 to the lungs to be exhaled. Hemoglobin is made up of amino acid chains that contain heme in each quadrant. Heme has an iron ion that can accept O2 in the right conditions. When oxygen binds to one of the 4 available positions in the hemoglobin will adjust its shape to increase the likelihood that oxygen will bind to another position. This is known as cooperative binding. The way that hemoglobin gets oxygen to deliver to the tissues is through the lungs. Specifically, the lungs will draw in the air and fill special sacs known as alveoli. These alveoli are in contact with capillaries. This increases the oxygen in the area, which increases uptake of oxygen onto the hemoglobin of the red blood cell. It will then leave through the pulmonary vein, where it gets pumped through the heart and delivered throughout the body. When the red blood cell finds its way to a capillary bed, oxygen will release from the hemoglobin. This will make room for carbon dioxide given off by the tissue to bind to the hemoglobin. The red blood cells will leave the capillary bed, where it will then travel through the vena cava, back through the heart, where it will be delivered back to the lungs. Here, the carbon dioxide will be dropped off into the alveoli, and more O2 will be picked up. The carbon dioxide is then breathed out through the lungs. What causes the oxygen to drop off the hemoglobin when it gets to the tissue is based on the environment around the red blood cell. When the red blood cell goes through the capillary bed, the tissues are giving off substances that change the affinity for O2 to bind to hemoglobin. For example, when the tissue gives off carbon dioxide, this increases carbon dioxide in the environment. This will cause the O2 to detach from the hemoglobin due to a change in the hemoglobin shape. This provides room for carbon dioxide to bind. Other things that change the affinity for O2 to bind to hemoglobin are the pH, the temperature, and 2,3-biphosphoglycerate. All of these act as an allosteric inhibitor. CO2 is created in the body. More specifically, during the production of ATP, the mitochondria will give off CO2 as a byproduct. Carbon dioxide will be released from the tissue and increase the levels of CO2 in the area. This excess CO2 causes hemoglobin to change its shape, which causes O2 to detach from the hemoglobin. It inhibits the binding of O2 to the hemoglobin. The more CO2 there is in the environment, the less O2 will bind to hemoglobin. This also means that the less CO2 in the environment will allow for more O2 to stay bound to the hemoglobin. pH also has an effect on inhibiting the binding of O2 to hemoglobin. There are different ways the body's acidity changes. For example, the CO2 that is given off from the tissue because of the production of ATP can mix with H2O in the area. This creates H2CO3. H2CO3 can give off one of its protons. This means that HCO3 is formed, specifically HCO3- and a proton. That proton causes the area to become more acidic. The more acidic the environment becomes, the less O2 will bind to hemoglobin. The more basic or alkaline the environment becomes, the more O2 can bind to hemoglobin. Temperature also has an effect on the affinity of O2 to binding to hemoglobin. The higher the temperature, the less O2 will bind to hemoglobin. The lower the temperature, the more O2 will bind to hemoglobin. This is useful, for example, when working out. If you are working out a specific muscle, the area will start to warm up. The ATP will be more consumed in that area, and so more ATP will need to be made. This means more CO2 in the area. Between the CO2 increase, the acidity increase from more CO2, and the temperature rise, this creates a prime area to drop off a large portion of O2 being held by the hemoglobin. Biphosphoglycerate also inhibits the binding of O2 to hemoglobin. The more biphosphoglycerate, the less O2 will bind to hemoglobin. That being said, without biphosphoglycerate, hemoglobin would be significantly less efficient. It would only drop off roughly 8% of the O2 being carried by hemoglobin, in comparison to its roughly 20% on average. When looking at this curve, we are looking at the saturation percent of oxygen on hemoglobin and comparing it to the partial pressure of oxygen in millimeters of mercury. We can see that after reaching about 80 to 90 millimeters of mercury, the saturation percent maxes out at about 98%. No matter how much more partial pressure of oxygen there is, there will be no more gains to the amount of hemoglobin saturated with oxygen. We can also see that in the areas of the body where the partial pressure of oxygen is about 40 millimeters of mercury, also known as resting tissue, there is about a 70 to 75% saturation of hemoglobin. This can be compared to 104 millimeters of mercury, which is the partial pressure for alveoli and the systemic arterial blood, which has a saturation level of about 98%. If we subtract 75% from 98%, we can see that 23% of the oxygen will be unloaded from the hemoglobin to the tissue. These curves can experience a shift depending on the changes in the environment. For example, a shift to the right is known as the Bohr effect. This is when the affinity of oxygen is inhibited when it comes to binding to hemoglobin. This could be an increase in CO2, pH, biphosphoglycerate, and or temperature. A shift to the left is known as the Haldane effect. This is seen where there is a reduction of CO2, temperature, pH, and or biphosphoglycerate. It also can be seen in areas that have an increase in oxygen compared to the others. In this curve, we're still seeing the saturation percent of O2 on hemoglobin versus the partial pressure of oxygen in millimeters of mercury. But we can also see the Bohr effect and the Haldane effect. We can see these effects to the affinity of oxygen to hemoglobin and what can change that. We also see how much the saturation of O2 to hemoglobin can change based on these shifts. For example, looking at 20 millimeters of mercury, we can see that the Bohr effect is sitting around 15% saturation. For the normal dissociation curve, it is about 30% saturation at 20 millimeters of mercury, while with the Haldane effect, it is close to 60% saturation. These shifts have a big effect on how much O2 is unloaded from the hemoglobin when delivering to the tissues.